Hi everyone! Today we're starting Unit 10, and today's lesson is an introduction to sequences, series, and summation notation. We have a lot of objectives for today, and our objectives are that students will be able to define sequence, finite sequence, infinite sequence, recursive formulas, explicit formulas, and series. You will be able to use term notation. You will be able to relate sequences to linear functions, and recognize and use summation notation. Let's get started. Alright, the first thing that I want you to be able to do today is define sequence. So what is a sequence? A sequence is a set of numbers with a particular order or pattern. Each number is called a term. So a sequence is a set of numbers with a particular order or pattern, and each number in the sequence is called a term. So make sure you copy this down in your notes. Pause your video if you need to. Otherwise, we're going to move on. A finite sequence is a sequence with a limited number of terms. Alright, a finite sequence is a sequence with a limited number of terms. So for example, this sequence right here, if we have our brace, 1, 2, 3, 4, 5, we end it. This is a limited number of terms. It ends. It doesn't go on forever. It is a finite sequence. Alright, make sure you have this definition written down. Pause your video if you need to. Otherwise, let's move on. An infinite sequence is a sequence with an unlimited number of terms, not ending. It never ends. So an infinite sequence is a sequence with unlimited terms. It never ends. So for example, if we had this sequence right here, 0, 1, 2, 3, 4, 5, and this ... means that it goes on forever. Alright, this would be an infinite sequence. It's a set of whole numbers, but it goes on forever. It never ends. Make sure you've got this written down. Pause your video if you need to. Otherwise, we're going to move on to term notation. Alright, so term notation is the notation that we're going to be using for this whole unit, so we need to be familiar with term notation. In term notation, the first term in a sequence is denoted as A sub 1. Alright, so we say A with a subscript 1. That means the first term of the sequence. Each subsequent term is denoted A sub n, where n is the term number in the sequence. So for example, if we're given this sequence right here, 1, 5, 9, 13, 17, and we want to identify the following term values. A sub 1 means what is the first term. So A sub 1 would be our first term, and the first term in this sequence is 1. So A sub 1 is 1. Now A sub 4, or the fourth term, would be 1, 2, 3, 4. This is our fourth term. So A sub 4, or the fourth term, is 13. Now, if we wanted to continue this sequence, we can look for a pattern, and we see that every term is going up by 4. We're adding 4 to the previous term to get the next term. So 13 plus 4 gives us 17, right? Now, 17 is our fifth term. So our sixth term would be 21. Add 4, then we get 25. Add 4, we get 29. Add 4, then 33. And if we keep going, 37, 41, 45. And it can go on for quite a while here. Alright? But if we want to count our terms, right? We've got our first term, second term, third term, fourth term, fifth term, sixth term, seventh term, eighth term, ninth term. So our A sub 9, or our ninth term, is 35. 3. All right, so 33 is our A sub 9, or our 9th term, okay? And then 37 would be our 10th term, 41 is our 11th, 45 is our 12th term. So A sub 12, or our 12th term, is 40. Oops, why did I write 42? It's 45. All right, so 12th term is 45. If you have any questions on any of this so far, please raise your hand, call me over so I can help you. Otherwise, let's move on. All right, another thing I want you to understand today is that sequences are functions as well. So each term value is paired with exactly one term number, and therefore a sequence is a function with these following properties. All right, so we can think of sequences as functions. The domain, or our n, right, that is the set of term numbers. So for example, our domain is n. This is the first term, second term, third term, fourth term, fifth term. Those are our term numbers. Now the range is the set of term values. So A sub n, this is our first term has a value of 1. Our second term has a value of 5. Third term has a value of 9. Fourth term has a value of 13. Fifth term has a value of 17. In an infinite set, the domain is the set of natural numbers. So that's the important thing we need to know about infinite sets. All right, they're always a set of natural numbers. All right, another definition that we're going to learn today is recursive formula. So a recursive formula is a rule in which one or more previous terms are used to generate the next term. So recursive formula, a rule in which one or more previous terms are used to generate the next term. So in recursive formulas, we use the previous terms to help us get the next term. That's all a recursive formula is. Now, one of the most famous recursive formulas is the Fibonacci sequence. And the Fibonacci sequence looks like this. It goes 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. Does anybody see a pattern here? All right, so if you're looking at the Fibonacci sequence, look for a pattern. In this sequence, we say that A sub 1, or our first term, is 0, and A sub 2 is 1. All right, so our second term is 1. So we've got our first term and our second term. And if you can see the pattern here, you see what you do is you take the first term plus the second term is going to give you the following term, the next term. So 0 plus 1 gives you 1. Then we take 1 plus 1 gives you 2. 2 plus 3 gives you 5. 5 plus 8 gives you 13. Then we go back. 8 plus 13 gives you 21. Go back. 13 plus 21 gives you 34. So what you're doing is you're saying that A sub n, or the nth term, is equal to the second term plus the first term. Because if we're saying n minus 1 means if n is 3, if we're looking for the third term, right? We're looking for A sub 3, our third term. Then n sub 1, where n is 3, that would be our second term plus our first term. So what we're doing is we're taking the previous term and the term before it, adding it together, and it's giving us the following term. This is a very famous recursive formula, the Fibonacci sequence, all right? So that's why I wanted you to recognize this. And all recursive formulas are similar to the Fibonacci sequence in that they use the previous terms to get the following term. All right, let's do some examples on recursive formulas. So number one, we've got our directions are to find the first 5 terms of each sequence. So here we're given our first term. Our first term is 14. and we're given our formula, our recursive formula, our rule. So our rule is saying that the nth term is equal to the previous term plus 9. All right, so anytime you have a n minus 1, this means the previous term, so the term that comes right before it. So what we're going to do in order to find the second term, so in order to find a sub 2 or a second term, we want to take the first term and add 9. And we know that the first term is 14. So 14 plus 9 gives us 23. So 23 is our second term. Now to find the third term, we want to take the second term, add 9. Our second term was 23, add 9, and we get 32. All right, now you don't need to write all this out if you understand what the rule is saying. However, if you get confused, write it out, all right? You may need more space than what's there in your box, all right? But just take out another piece of paper and write it out. But if you understand what's happening here, we see that we're just taking this term, adding 9 to get the next term. So in order to get the fourth term and the fifth term, just add 9. So 32 plus 9 is going to give us 41. Oh my goodness. It's going to give us 41. So that's our fourth term. And then our fifth term is 50. So we're just adding 9 to the previous term. We do 41 plus 9 gives us 50. Then you always want to write your sequence in the little braces, right? So we write our brace, start with our first term. We've got 14, 23, 32, 41, 50, end our brace, and this is the first 5 terms of our sequence. All right, number 3. So number 3 is a little bit more complicated of a recursive formula. So for this one, you might want to write out every step, all right? At least right now in the beginning when we're just learning, we definitely want to write these out. And I know there's not enough space to do it in your box, all right? That's in your notes. So if you need to do it off to the side, if you need to go into number 4, that's okay, all right? I'm just warning you, there's not going to be enough space in your box for this. So number 3. We're given that our first term is 354, and we're given a rule here. We're saying that the nth term, or the next term, is equal to the previous term plus 6 divided by 3. All right, for n is greater than or equal to 2. Because we're given the first term, we want n, or the term number, to be 2 or more. So we want the second term, the third term, the fourth term, and so on and so on. All right, so to find the second term, where n is 2. We take the previous term, which is our first term, and we know that that's 354 because we're given it, add 6, and then divide by 3. So 360 divided by 3 gives us 120. So 120 is our second term. To find our third term, we want to take the second term, which we just found is 120, plus 6 divided by 3. So we get 126 divided by 3. Plug that into our calculator and we get 42. So 42 is our third term. To get our fourth term, take the previous term that we just found, 42. Add 6, divide by 3. 48 divided by 3 gives us 16. Then our fifth term, we do our previous term we just found, plus 6 divided by 3, 22 divided by 3, and we're just going to leave it as an improper fraction, 22 thirds. All right, if you wanted to put in a decimal, you can. It's just easier. Why do the extra work? 22 thirds is the more accurate answer. All right, now we want to write our final answer as a sequence with our braces. So our first term was 354, then 120, 42, 16, and 22 thirds. And that's our final answer. All right, now you may see problems that look like this, where you're given a sequence and you're asked to write a rule for the sequence, and then to give the next three terms. Now for these, there's no real formula, no real straightforward way of doing this. This is going to require those critical thinking and logic skills, all right? You got to use your brains here, analyze the sequence, and look for a pattern. So this calls for some staring at the numbers, looking for a pattern, using those critical thinking skills. So if we're looking at this sequence, we see that it goes from 4 to 11 to 32 to 95 to 284. Start with the smaller numbers because it'll be easier to recognize a pattern with smaller numbers. So we see that we go from 4 to 11, 11 to 32. Now, what I notice here, all right, hopefully you see it too, is that we triple this, subtract 1, and we get 11, right? 4 times 3 minus 1 gives us 11. And that same rule applies if we go from 11 to 32. 11 times 3 minus 1 gives us 32. So the easy way to do it is look at the first three terms to help you figure out that rule. All right? So our rule here is that we triple the term, minus 1 gives us the next term. So in order to write a rule for this, we have to first say, what is our first term? Our first term is a sub 1 equals 4. That's our first term. And then the rule for this, we have to write it in term notation. So we say a sub n equals 3 times our previous term, 3 times a sub n minus 1. This means 3 times our previous term minus 1. And that is our rule for the sequence. That's our recursive formula. So this would be part of our answer. And then in order to find the next three terms, all right, so we're given the first 5 terms, we want to find A6, A7, and A8. All right, 6th term, 7th term, and 8th term. So to find the 6th term, we want to do 3 times the 5th term. So 3 times 284 minus 1, that's going to give us 851. Now to find the 7th term, 3 times the previous term, which we just found was 851, minus 1. Plug that into our calculator, do multiplication first, then subtract the 1, 2,552. Then our 8th term, we do 3 times the previous term we just found. Multiply these together, then subtract 1, and we get 7,655. And that's our 8th term. So there's our next 3 terms in the sequence. All right, if you have any questions so far on anything we've learned up to this point, please raise your hand, call me over so I can answer your questions. Otherwise, let's move on to explicit formulas. All right, so here's another definition that we need to know. So an explicit formula, so before we learned recursive formulas where the previous term mattered and we used the previous term to get the next term. That was recursive formulas. Now we're learning explicit formulas. And an explicit formula is a rule in which the nth term or the following term is defined as a function of n. The previous terms are unnecessary. So an explicit formula is a rule in which the nth term is defined as a function of n. The previous terms are unnecessary. So the important thing to remember with explicit formulas is that we do not need the previous term. The previous term does not matter. All right, recursive, previous term matters. Explicit, previous term does not matter. All right, now let's go through some examples of when we use explicit formulas. All right, so number 7 is an explicit formula, and our directions are to find the first 5 terms of this sequence. All right, it's still a sequence, and we think of it as a function, right? 7 times n minus 3. This is a linear function. In order to find the nth term, we plug n in, all right? And that gives us the nth term. So, for example, if we want to find the first term, So the first term would be a sub 1. This is our first term, and in this case, n equals 1. So we plug 1 in for n. So we say 7 times 1 minus 3. N equals 1 because we're talking about the first term. So then we just simplify 7 times negative 2, and our first term is negative 14. Now to find our second term, a sub 2. We say 7 times n equals 2. 7 times negative 1, we get negative 7. A sub 3, or our third term. So now n equals 3. We're just plugging n in to get the nth term. 7 times 0, third term is 0. To get the fourth term, we plug 4 in for n. 7 times 1 gives us positive 7. And to find the fifth term, we get 7 times n is 5 now. So the fifth term is positive 14. Now we always want to write this as a sequence. Alright, so we want to write it in the braces. So the first 5 terms of the sequence would be negative 14, negative 7, 0, 7, and 14. And that would be our final answer. Alright, number 9 is the same idea as number 7. It's still an explicit formula. The previous term does not matter. So, in order to find the first term, n becomes 1. So we want to be sure to use parentheses here. So we would say negative 4 times 1 squared. Always do your exponents first. So we get negative 4 times 1. First term is negative 4. Then a sub 2. Now n is 2. Remember to do your exponents first. So we get negative 4 times 2 squared gives us 4. Second term is negative 16. A sub 3. Negative 4 times 3 squared. So we get negative 4 times 9. Negative 36. A sub 4, fourth term. Negative 4 times 4 squared. Negative 4 times 16 is going to give us negative 64. And last but not least, the fifth term, negative 4 times 5 squared. So negative 4 times 25 gives us negative 100. Oops. All right, now we want to remember to write it as a sequence. So our final answer, we put it in braces. First 5 terms of the sequence would be negative 4, negative 16, negative 36, negative 64, and negative 100. And that's our final answer. Alright, I want you to try to do number 11 all on your own. Alright, find the first 5 terms of this sequence. When you come back, I'll have the answer written on your screen and we will go through it. So go ahead and pause your video now. Alright, so you should have gotten the first 5 terms of this sequence are 1, negative 2, 4, negative 8, 16. If you didn't, stay tuned for the explanation. If you did get this answer, you can fast forward through this and move on to the next problem. Alright, so how did we get these first 5 terms? So start with a sub 1, right? So we're looking for the first term. That means we're going to plug 1 in for n. So we plug 1 in for n, so we get parenthesis negative 2 to the 1 minus 1 power. This is negative 2 to the 0 power, and anything to the 0 power gives us 1. For the second term, plug 2 in for n. So negative 2 to the 2 minus 1 power. Negative 2 to the first power gives us negative 2. Anything to the first power is just itself. Third term, plug in 3. So we get negative 2 squared. Negative 2 times negative 2 gives us positive 4. Fourth term, plug in 4. So we get negative 2 to the third power. Anytime we've got negative and odd exponent, we end up with a negative answer because we're saying negative 2 times negative 2 gives us positive 4 times negative 2 gives you negative 8. Fifth term, we plug 5 in, we get negative 2 to the 4th power. That gives us positive 16. Remember, when the parentheses are around the whole thing, that means we're raising the entire negative number, negative integer, to that exponent. We don't just say 2 to the 4th power, then add the negative. When we would do that, if it was just negative 2 to the 4th power, this is when we would first do 2 to the 4th power, which is 16, then add the negative. All right? But because there are parentheses around the whole thing, we do negative 2 to the 4th power. All right, if you have any questions on this, please raise your hand, call me over. Otherwise, let's move on. All right, now problem number 13. We've got a sequence, and we're going to have an explicit formula here, which means the previous term doesn't matter, but we need to write a rule for it. All right, so this is another one of those where we have to use our critical thinking skills, analyze, look for a pattern. All right, so what we want to do is start by labeling these as the first term, the second term, the third term, the fourth term, the fifth term. So when we're saying A1, right, the first term, that means n equals 1. A sub 2, or second term, means n equals 2, and so on and so on. All right, negative 11, n equals 3. All right, so in order to look for a pattern here, what we want to do is try to come up with a rule that works for every single term. So what we want to do is say, all right, if negative 7 is the first term and negative 9 is the second term, what if we multiplied n by something and subtracted something, right? Look for a pattern here. We know that it's going down 2 every time, all right? But we can't just say n minus 2 because we've got, if we said that, that would be n is 1, right? But we've got to use n in our rule. Now, what if we took n, multiplied it by negative 2, and subtracted 5. So if our first term is negative 7, okay, and we said negative 2 times n, so we multiply our n, which is 1, by negative 2, and then subtract 5. That's going to, if n equals 1, we get negative 2 minus 5 gives us negative 7. So that rule works for our first term. Let's see if it works for our second term. All right. For our second term, if n equals 2, if we plug 2 in, so 2 times negative 2 gives us negative 4, minus 5 gives us negative 9. It works for our second term. Our third term, if n equals 3, 3 times negative 2 gives us negative 6, minus 5 gives us negative 11. That works. All right, so our rule could be a sub n, so the nth term equals negative 2 times the term number minus 5. All right, and there's no real easy way to do this other than look for a pattern, all right, and come up with a rule for it. I would never give you a super complicated one on a test. I just want you to be able to use your critical thinking skills here, and you're going to practice these a lot to try to come up with a rule for the sequence, all right? And if we wanted the next 3 terms, that's actually much easier, right? Because we know it just keeps going down by 2. So the next 3 terms would be negative 17, negative 19, negative 21, all right? That's actually much easier than coming up with the rule. All right, number 15, we've got another sequence here. We've got our first term is 2, second term is 5 halves, third term is 3, fourth term is 7 halves, fifth term is 4. All right, and we need to come up with a rule. So the numbers I just wrote in blue are what your n equals. That's your term number. The numbers that are written in our sequence are our term value. So we want to think of it as a function. all right? And if we think of it as a function, all right, we want to look for a pattern here, all right? What is it going up by? So if we're looking for a pattern here, we see we've got 2, 3, 4, right? We've got 2, 3, 4 here. We've got 5 halves, 7 halves. So our first term is 2. Our second term, all right, in order to get this, we would say n plus 3 divided by 2 gives us this, right? N plus 3 divided by 2 gives us this. That would work here, right? And if we said n, 1 plus 2 divided by 2, that gives us 2. 3, n, which would be 3 plus 2 divided by 2, gives us 3. Let's see if this works for all of them. So if we said a sub n, our nth term, is n plus 3 divided by 2. We're adding 3 to the term number, dividing by 2, and that gives us the term value. All right, and this rule works for this one. All right, another way to think of it is think of it like a linear function, and you've got a slope and a starting point, right? So our slope here, what is it increasing by? It's increasing by 1/2 every time, right? It's going up 1/2 because 2, 5 halves is 2.5, 3, 3.5, 4, 4.5, 5. So our slope would be 1/2. That's what it's increasing by, our rate of change. Now, our starting point, we would need the 0 term, right? So if it's going up by 1/2, that means our starting value would be 3 halves, right? Or 1.5. So our b would be 3 halves. If we plug this into y equals mx plus b, all right, what we get here, we would say y equals 1/2 x plus 3 halves. All right, and we want to try to write this as a single fraction to make it a rule. So we change this to x over 2 plus 3 over 2, which becomes x plus 3 divided by 2. And that looks awfully familiar. All right, that's what we've got written over here, but we change the x to an n, and instead of y, we say a sub n. All right, this actually would work for number 13 too. You could do the same thing. If you can't recognize the pattern, think of it as a linear function, all right? So for number 13, you could have said, all right, it's decreasing by 2 every time, so our b, or our starting value, would have been -5, and our slope is -2. So that's how we get the -2n minus 5, all right? So that would have worked for number 13 as well. So if you can't recognize the pattern, think of it as x values, y values as a linear function, write it in slope-intercept form, and that'll give you your explicit formula, all right? Just another way of doing it. In math, sometimes we can use those critical thinking skills, and sometimes there's always a nice, clear-cut mathematical way, all right? We like clear-cut mathematical ways. So we do need the next 3 terms. So if we're adding 1/2 every time, our next 3 terms would be 9 halves, or 4.5, then 5, then 11 halves, or 5.5. And that would be our next 3 terms. All right, I know the notes are a little long today, and I apologize, guys, but there's just so much to cover today, so many definitions I want you to know, and this just kind of gives you a good overview and introduction on sequences and series, all right? So now, a series. A series is the sum of the terms in a sequence. So it's when we take a sequence and we add all the terms together. So, for example, if we've got this sequence right here, 1, 2, 3, 4. In order to find the series, we would just say 1 plus 2 plus 3 plus 4. Add them together and you get 10. So the series is 10. Now, this one right here, we've got 3, 6, 9, 12, and this ... can be a little deceiving, all right? So it's increasing and it goes on forever. So if we keep adding bigger numbers together, it's going to get bigger and bigger and bigger and bigger. So we would call this an infinite series, and we would use the infinity symbol because it's going to get infinitely bigger, always going to be an infinite series. Now, this one right here, it's going down, it's decreasing. All right, we've got 1/2, 1/4 is smaller than 1/2, 1/8 is smaller than 1/4, 1/16 is smaller than 1/8, and this ... means that it goes on forever. So because it's decreasing and it goes on forever, we say that this series adds up to 1. The sum of this sequence would be 1. All right? So anytime it's decreasing and goes on forever, the series equals 1. All right, so now anytime we've got one of those infinite series, right, where we've got a sequence that goes on forever and it's increasing, we can find what's called partial sums. So a partial sum is denoted by S sub n. This means partial sum. This is the notation we use. And the definition of a partial sum is the sum of a specified number of terms. Okay? So we take a certain number of terms in a sequence, add them together. That gives us a partial sum of those infinite series. So our directions are to find the partial sum for each given sequence. And here we're given 1, 2, 3, 4, 5. We're looking for the sum of the first 9 terms. That's what S sub 9 means that we want the sum of the first 9 terms. So we've got the first term, second term, third term, fourth term, fifth term. We see that it's increasing by 1 every time, so the 6th term is 6, the 7th term is 7, the 8th term is 8, the 9th term is 9. So all we would do is add them together. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. So we get that the partial sum of this, or actually S sub 9, equals 45. And that would be our final answer. Just add them all together. All right, number 3, we're given the first, second, third, fourth, and fifth terms, and we want to find the sum of the first 6 terms. S sub 6 means the sum of the first 6 terms. Now, looking for a pattern here, we see that these are all perfect squares. We've got 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So our 6th term is going to be 6 squared, or 36. All right? Now we add them all together. 1 plus 4 plus 9 plus 16 plus 25. So the sum of the first 6 terms, plug it in our calculator, we get 91. And that's our final answer. All right, now summation notation is very important. So this is the correct notation that we use to show summations, or in this case, series. When we're adding together all of the sequences, we get a series, we use summation notation. So in summation notation is just a way to represent a series using the Greek letter sigma. All right, this little E is the Greek letter sigma, and that denotes the sum. So anytime you see the sigma symbol, this means the sum. Now, the number on top, this 5 in this example, the number on top is always going to be your last term. And the number on bottom always means the first term. So with n equals 1, we're saying the first term to the 5th term is what we're looking for. And this right here is going to be the formula for the sequence. So this is going to be like your function. What are you using? Could be a recursive formula, could be an explicit formula. All right, so what follows the sigma is always your formula for the sequence. So in this example, our formula is 2 times the term number, and we're going from the first term all the way up to the 5th term. So if we wanted to find the sum of the series above, we would need to say 2 times the first term, because we're starting with the first term, plus 2 times the second term, plus 2 times the third term, plus 2 times the 4th term, and our final term is going to be the 5th term, because that's the number on top. That's our last term. So 2, now we're just simplifying, plus 4, plus 6, plus 8, plus 10. We add all these together, and we get 30. So the summation, or the series here, all right, if we see it's in summation notation, our final answer, the sum of the series above, equals 30. All right, so now we want to expand each series and evaluate. So when we're expanding, we're taking it in summation notation and we're writing it out, all right? So for example, this one, we're saying the summation of n minus 1 from the first term to the 12th term, all right? So we want to write this out. So what we're saying is we're saying from the first term, so our first term is when n equals 1, so 1 minus 1. Plus, because we're talking about the summation of the sequence or the series, plus the second term when n equals 2, 2 minus 1, plus the third term, 3 minus 1, plus 4 minus 1, plus 5 minus 1, plus 6 minus 1, plus 7 minus 1, plus 8 minus 1, because we're going all the way up till 12. 9 minus 1, 10 minus 1, 11 minus 1, plus 12 minus 1. All right, we're going when n equals 1 all the way up to 12. Now, simplify this so we get 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11. All right, so this is expanding out that series. We're taking it from the summation notation. Now we've got something we can plug into our calculator, something that looks a little bit more normal. All right, going from this fancy Greek summation notation to just simple add them together. So we add these together and we get that our final answer is 66. All right, 0 plus 1 plus 2 plus 3 all the way to 11 gives us 66. All right, I want you to try number 7 on your own, expand the series, and evaluate, all right? When you come back, I'll have the answer written on the screen, and we will go through it together. So go ahead and pause your video now. All right, so for number 7, you should have gotten 58. So what we're doing here, our formula is 5 times the term number plus 2. And we're saying from k equals 1 all the way till 4. So we're saying the first term, second term, third term, plus the fourth term. Add them all together. So we plug in 1 for k. We plug in 2 for k. We plug in 3 for k. Plug in 4 for k. Then we simplify all these. Always do multiplication first. Multiplication first. 5 times 3. 5 times 4. Then add them together. All right? Then take your numbers, add them together. Final answer is 58. All right, if you have any questions on this, please call me over. Let me help you because it's about to get a tiny bit more complicated. So if you're not understanding it now, please, please, please call me over so I can help you. Otherwise, let's move on. All right, we're going to skip number 9 just because it's pretty much the same thing as number 7. All right, you should have gotten a final answer of 70. All right, so your final answer should be 70. If you want to go ahead and try it on your own, see if you get 70. Awesome. All right, otherwise we're just going to move on because it's so similar to number 7 and this is such a long video already and I want to just teach you something I haven't taught you yet. All right, so let's move on to number 11. All right, number 11 is slightly different from the previous problems because now we're saying from 2 to 6, all right? In all the previous problems, it was always n or m or k equals 1, all right? But now we're starting at the second term. Doesn't change it very much, all right? But it looks slightly different, so I didn't want you guys to freak out, and I wanted to do this one with you, all right? So all we're doing is we're starting with m equals 2. So our first term in this series is when m equals 2. So we say 2 squared minus 1 plus, now we're going from 2 to 6. So then we go to 3 squared minus 1 plus 4 squared minus 1 plus 5 squared minus 1 plus 6 squared minus 1. And we're done because the number on top of our sigma is 6. So that means we stop when m equals 6. That's our final term. Then we're just simplifying. All right, so 2 squared gives us 4. 4 minus 1 gives us 3. 3 squared gives us 9. 9 minus 1 gives us 8. 4 squared is 16, minus 1 gives us 15. 5 squared gives us 25, minus 1 gives us 24. Then we've got 36 minus 1 gives us 35. Then we just add them all together. Final answer is 85. All right, last but not least, our final example for the day is number 13. And now this one looks slightly different as well because we've got something in front of our summation notation. All right, in front of our sigma. Now, what I want you to do, anytime you see one like this, immediately draw brackets around the sigma, around the summation notation. So what you're going to do is solve what's inside those blue brackets like normal and then multiply it by 1/2. All right, so we've got 1/2, we leave it on the outside, and then we want to solve it just like we were doing before. So we're going from 2 to 4, so we start with x equals 2. 2 squared minus 5, plus 3 squared minus 5, plus 4 squared minus 5, and the number on top of the sigma is 4. That means 4 is our last term. All right. Now we solve this like normal. All right, so we leave the 1/2 on the outside. Then we do 2 squared gives us 4, minus 5 gives us -1, plus 9 minus 5 gives us 4. 16 minus 5 gives us 11. We've got 1/2 times. We do -1 plus 4 plus 11 gives us 14. Now we just do 1/2 times 14, or 14 divided by 2 gives us 7. And that's our final answer. All right, and that concludes our Day 1 notes, nice introduction on sequences and series. I apologize for it being a little bit long today, but we covered a lot of new definitions, a lot of new information, and hopefully that gave you a nice overview of everything. All right, the rest of this unit, we're just going to dive deeper into what we learned today. All right, so if you have any questions, please raise your hand, call me over so I can help you. Otherwise, look to the board to see what to do next, and I hope that you have a great day.